All right, picture this. You're in your first big programming interview. You've gotten through the small talk, and the interviewer leans forward and hits you with the first real question.
Okay, so let's dive right in. The challenge is simple. Take a giant list of numbers and sort it as fast as humanly possible. What's your answer?
Now, you probably know that some algorithms like bubble sort are just a non-starter for a million items. They're way too slow. The standard library in pretty much any language uses a super optimized quicksort, and it's fast. It's a great answer. But the question was, what's the most efficient way? Can we actually beat the standard? Oh yeah, we can, by about 7 times actually. To see how we get there, we've got to start with a much simpler version of the problem first. This is going to lay all the groundwork for the really cool solution. So forget 32-bit integers for a moment. Imagine you had to sort a million numbers, but they were all just single digits, 0 through 9. Well, the fastest and, honestly, most intuitive way to do this is with an algorithm called bucket sort. The logic here is just incredibly simple. You just make 10 empty buckets, one for each digit. Then you go through your list and you just drop each number into its matching bucket. So all the zeros go in the 0 bucket, all the ones go in the 1 bucket, and so on. Then you just read them back out in order, and that's it. You have a perfectly sorted list. And for these small ranges, bucket sort is ridiculously fast. For 8-bit and 16-bit numbers, it just blows quicksort out of the water. We're talking about 15 times faster. So you're probably thinking, why don't we just use this for a 32-bit problem? Well, take a look at that last row. A 32-bit integer can have over 4 billion possible values. That means we'd need 4 billion buckets. That's a whopping 16 gigabytes of memory just to hold the buckets. And then we'd have to loop through all of them. The performance just completely falls off a cliff. So it seems like a dead end. Or is it? We were so close. Bucket sort is blazingly fast for 16-bit numbers. What if we could somehow use that insane speed to solve our much bigger 32-bit problem? This question leads us to the absolutely ingenious idea behind Radix sort. Now here's what's so wild about this. The solution is completely counterintuitive. Think about it. If I asked you to sort a list of 2-digit numbers, your brain would instantly start sorting by the first digit, right? The most important one. Radix sort does the exact opposite. It starts with the least important part, the digit on the right. It feels totally backward, but there's a secret that makes it all click into place. And that secret is a special property called stability. A stable sort, which bucket sort just so happens to be, promises one simple thing. If 2 items are considered equal, it will keep them in their original order. So let's say you have 71 and 78. If you sort them by their first digit, which is 7 for both, a stable sort guarantees that the 71 will still come before the 78 in the result. This right here, this is the whole key. Let's just watch how this works. First, we do a pass with bucket sort, but only on the rightmost digit, the least significant one. The list gets all shuffled up, and it doesn't look sorted at all yet. But here's the magic. We take that newly ordered list, and we do a second bucket sort, but this time on the most significant digit. And bam! The final list is now perfectly, completely sorted. So why on earth does this work? Well, that first pass, where we sorted by the ones place, it's like we set up a tiebreaker in advance. So when we get to the second pass and sort by the tens place, all the numbers that start with a 1, like 12 and 19, they get thrown into the 1 bucket. But, and this is the kicker, because bucket sort is stable, they stay in the relative order we just gave them. 12 stays before 19. We basically pre-sorted each little group before we even grouped them. It's so clever. And this idea scales up beautifully to solve our original interview problem. We just take each 32-bit integer and mentally split it into 2 16-bit chunks. We treat them like 2 digits in a really, really big number system. Then we run our super fast 16-bit bucket sort on the least significant half, and then we run it again on the most significant half. That's it. 2 simple passes, and the entire million-number list is perfectly sorted. So let's see what happens when we put this specialist algorithm up against the generalist, quicksort, in a real-world test. The results are pretty staggering, honestly. For our specific problem, sorting a million 32-bit integers, Radix sort is consistently about 7 times faster than the highly optimized quicksort you'd find in the standard C++ library. I mean, that is just a massive, massive performance win. Which, of course, brings up the most obvious question, right? If this thing is so much faster,
Why isn't Radix sort just the default algorithm that our computers use for sorting everything?
Well, there are two really big reasons. First, Radix sort has a high fixed cost. It always has to loop through all 65,536 of its buckets, even if you're only sorting like 10 numbers. So for small lists, say under 10,000 items, Quicksort is actually faster. And second, and this is the big one, Quicksort is a generalist. It's like a Swiss Army knife. It can sort anything you can compare, strings, objects, whatever. Radix sort is a specialist. It's a scalpel built just for numbers. Okay, so it seems pretty clear. Radix sort is for integers, Quicksort is for everything else, like floating point decimal numbers. Radix sort can't sort those, right? Well, this is where we get to my absolute favorite programming hack of all time. So first, a super quick refresher. Floating point numbers are just the standard way computers store decimals. The bits inside are broken into three distinct parts: a sign bit for positive or negative, an exponent that sets the scale, and a mantissa that holds the actual digits. Now, here is the mind-bending part. Deep down in a computer's memory, everything is just ones and zeros. That exact same string of bits can be interpreted as a huge integer, or it can be interpreted as a floating point number like pi. It all just depends on the lens you use to look at the data. And this is where the genius comes in. The people who designed the floating point standard way back in the 80s were incredibly clever. They designed the bit format so that for any two positive decimal numbers, if number A is smaller than number B, its raw bit pattern, when you just read it as a plain old integer, will also be smaller. The order is perfectly preserved across interpretations. This means you can sort positive floating point numbers by just pretending they're integers and running our lightning-fast Radix sort on them. You don't even have to convert anything. So, the crucial point here is this. The standard library isn't slow because the people who wrote it made a mistake. Not at all. It's a general-purpose tool designed to reliably handle any situation you could possibly throw at it. But that amazing generality has to come at a performance cost. And that really leaves us with the big takeaway from all of this. Most of the time, the standard approach is good enough. But when performance is absolutely critical, if you really take the time to deeply understand the specific constraints of your data and your problem, you can almost always find a specialized tool that will blow the general-purpose one out of the water. So the real question is, where in your own work can you find that specialist's edge?